Hello, everyone. Thanks very much for being here. We hope that you're enjoying besides Munich after such a long lockdown. So our talk is going to be obviously about hacking. I mean, you guys can see the picture. There's two hackers on the slide. So let's start with the introduction. So who are we? I'm Javier. I'm a hardware security specialist on the embedded side. I am from Cádiz, from the south of Spain. I enjoy reverse engineering products because quite often, more than not, I'm disappointed with the features that devices have, and I always want to improve them myself, right? Like, why not if I can? And I do like cake when it's not a lie, as happens sometimes, and I do like barbecues. I mean, barbecues are good.
Hi, my name's Ethan Briggs. I'm from California in the U.S., and I just graduated from college about a year ago with a mechanical engineering degree and a math degree, but the math degree was more for fun, honestly. But over this last year, I've been able to work with Javier a lot, and I've been really lucky to work with him in automotive security engineering, specifically in the hardware and a lot of the embedded systems electricity parts, and I've been really lucky to have that. I'm looking forward to more.
So, why are we here?
Okay, well, current day car hacking has become kind of mainstream. You can see examples up there of people who post things like hacked on their dashboards. Like, look at me, I've done all this work or whatever, a car is hacked. That was mainly popularized in the 90s. That's CAN injection. It's not all that difficult, you can tell, because you can probably look up a guide for it and you could probably find something to do it in about 15 minutes or so. But further than that, the reason why it's so simple is because a lot of the mechanisms for security on the ECU are pretty simple, and they kind of they don't need to be, but they are because the ECUs are so lightweight and they are so resistant to noise, because they have to be. They're in cars, the cars are going to be jostling around, there's going to be a lot of noise. There has to be. I might have said that already. Whoops. But on the and this goes hand in hand with diagnostics, which are also pretty simple. Once you understand what they're doing, because they talk in exclusively codes, once you memorize them, you can read it like you read letters on this, or like you read words. What we'll be showing you specifically is 3 specific, what are the hacks?
Let's call them flaws in the implementations of the state machine for diagnostics, right? And to add to what Ethan was saying, these 2 pictures, I find them personally funny. You cannot see the hacked here, but it says hacked here, so you'll have to believe that one. Typically, these people start thinking that they can inject a CAN frame, and they put an ASCII string, right? So it shows up here. Now they're car hackers. And that's the first and the last tweet you see about car hacking that they make. Because automotive security is actually not as easy as just injecting. So let's talk a little bit about the automotive diagnostic protocols. This is just a heads up. We're not going to waste too much time on that. So the diagnostic protocols usually are based on a request-response scheme where the tester or the device that you connect to the car is a client, and the DUT, the device under test, which is the ECU, acts as a server, right? And then, like most things, not everything, unfortunately, it requires like certain authentication. It has security measures for some functionality, right? So, security access, which is going to be the target of our talk, which is the service ID 27 hex. It is the tool that's used most commonly to restrict functionality, right? So, such as if you want to update the firmware on an ECU, you will most likely, hopefully, need to perform a security access challenge response, right? The same thing if there are some things that could be critical, such as the bin, right? It should not be easy. It should not be easy to spoof the bin by just changing it, right? Or there might be some other operations which are restricted to the manufacturer, such as adding a new key fob. Like sometimes when your car, you have a key lost, or you need a new key, you have to go to the dealer, and then the dealer wants to charge you like 200 euros for adding a new key. right? That's because they have tooling that is specifically required to do that. Right. I mean, and security access is actually so relevant to automotive security that there's even a market for selling and buying security access algorithms.
Okay, so thank you. How the actual security access protocol works is you have the tester. You have the thing that talks to the ECU or the diagnostics ports, the DUT, the device under test. And it starts off with the tester sending a request for security access, which you can, there it is. Request for security access, which is that top left option right there. The DUT recognizes that, as you can see right here, it receives it, and then it generates a 32-bit random seed. This seed is random, and it's, once again, 4 bytes, which is important and will come into play later. Then sends that seed back to the tester, where the tester receives the seed, and both of them, they calculate, using an algorithm that is generally not known, a key that you will have to use to unlock it. It then proceeds to calculate the key, send it to the tester, or the tester sends it to the DUT. My apologies. And after it sends it to the DUT tests the key against the key that it calculated on its own. And if it's correct, it has 2 states that it goes into. It says either security access is granted, or on the other hand, if it was incorrect, they increment the wrong attempts counter and they don't give you access. Okay. This is important because, as I mentioned, they're kind of random, but more importantly, that changes based on your security level. And most likely based on the DUT. So if you're trying to get access to the very lowest level, you can generally get access, or you have 1 key for that, and then if you get access to the next one, a higher level, you probably won't be able to get access with the same key, and even then, they're oftentimes random. On top of that, the security access is oftentimes change based on what level of security that you want, which is a little bit different. But if you're going in for a default diagnostic section, hex 10, you might not be able to do some things that require a programming session.
Finish.
Which is hex 13, I believe.
Diagnostic session is 10. So to add something, and maybe this helps understand a little bit about the security access different levels. Think of a building, right? An office building. So, and all the doors have a key, like a physical key, like the one you guys most likely used to get in your house. So now there's going to be a, let's say, lower level, by lower, I mean like more restricted. So it would be the inverse if we're talking about actually reverse engineering. So a higher level key, which allows you access to a building. So you get into the building, that's a security access algorithm, right? Usually that's the most simple. So now you got that. So you got into the building. Now, once you're into the building, you can have access to different compartments, offices, right? Or rooms, if you wish. Now, the key for those rooms will be different. And you can obviously not attempt to open an office door if you're not already in the building, right? So that's what it means by switching different diagnostics modes. Diagnostics modes could be a standard session, which is 0-1, right? Then you can perform certain security access levels, which would be equivalent to getting inside the building. Then if you change to a extended session or a programming session, right? Which maybe you need to perform this security access before it allows you to change to that session. Then you could use a different, more secure, hopefully, security access algorithm, right?
And I also mentioned before that the wrong attempts counter incremented. This is important because that prevents brute force attacks. After you have 3 or so, it depends on the manufacturer, but then it locks down for generally 1 to 30 minutes. Just once again, prevent brute forcing.
So, just for the ones of you that are familiar with coding a little bit, we'll explain it nonetheless. This is, if you can read it, it might be a little bit too small, but I'll walk you guys through the code. This would be, so the first part of the security access challenge, right, response. So one thing that we need to mention is that security access is divided into two different parts. One is requesting the seed, and the other one is providing the key. They are separated. Usually you will see them one after the other, but you could very well request a seed, read the ECU bin, and then send the key. They do not need to be sequential. So what does the request seed do? This is the code from a DUT, device under test perspective. So you just provide like the data, which would be like the array that contains the label. So then the DUT checks for the label, because as we said earlier, ideally there would be different keys, different algorithms, right? Now, when it checks for the label, the first check it does is see if that security access label is locked because the tester had too many wrong attempts, right? So if it's locked, then it returns false. It tells like, yeah, see you later. Like, you've got to wait out the time. If it's not locked, then it will create a random number. Usually it's 4 bytes. I mean, there's different algorithms, right? But let's go with the standard. It will create 4 random bytes, and then it will just send those 4 random bytes. So that's as far as it goes for the requesting the seed part. Now, the second part, which is actually now the tester, as Ethan showed before, has calculated the reply, the response, and sent it. So the check key function, the verify, we call it here, again, will just use the seed that the ECU itself generated earlier, perform its own calculation, because obviously the ECU knows the algorithm, right? And then it would just compare if the result that it got is the same that the tester sent. Now, if it was the same, then, yep, all good, right? There you go. You got security access. If it was not correct, then it would increment the wrong attempts, right? Because remember, we got here because it wasn't yet locked. So what happens when you fuck up and you just like give the wrong reply? Wrong attempts increase.
So Hacker Kitty noticed something. I don't think I personally noticed it, but I trust him. He has a cool hacker hoodie on. He's just hacked the planet behind him. He seems like he knows what he's talking about.
Yeah, we'll see what the kitty found probably in a little bit.
Okay. So the next thing is man-in-the-middle attacks. Specifically, man-in-the-middle attacks similar to can injection. They're not really new. They were around in the 90s. They're used for a lot of attacks, and it's oftentimes very effective. But specifically because they were developed in the 90s, at the same time, KWP 2000 and UDS were also designed. So you might think that they may take into account this popular attack, but obviously you probably guessed by the fact that we're presenting on it, they didn't. It's still very widely used in current systems.
Yeah.
Which you can tell from security hijack, which was my apologies, presented on in 2016's Black Hat and DEF CON 24 by Javier about this attack, which uses man-in-the-middle on ECUs that are still being manufactured today. And it's a standard man-in-the-middle attack, and it has 3 steps to it. First of all, you forward all traffic from the tester to the DUT and from the DUT back to the tester until there was a security access. And then after that, the tester and the DUT go through the steps that I mentioned before about getting security access, and then it disconnects. And suddenly, without the tester there, you have all the security access that the tester just gave you, or would have had access to without the man-in-the-middle there.
So, to make it like perhaps easier to understand, with letters that even I can barely see, so I can only imagine like what you guys can see there. So let's imagine you can see them. So here, there's the tester side, there would be the man-in-the-middle attacker, there would be the DUT here, right? So tester sends the request for seed, right, for security access. The man-in-the-middle forwards that, doesn't touch. The ECU receives the request, so it generates a seed. That the man-in-the-middle attacker forwards it, doesn't touch. Now the tester gets the seed, it does its calculations, like we learned earlier. The man-in-the-middle attacker forwards the result. Now the ECU verifies the seed, and when the ECU sends a positive reply, and only when that happens, then the man-in-the-middle attacker kicks the tester, says goodbye, and takes over diagnostic session. So to the eyes of the DUT, the man-in-the-middle attacker and the tester are the same because there's like literally no validation, there's no authentication, there's nothing. So you end up having a secured diagnostic session, like having security access without needing to know the key or the algorithm. So let's talk a little bit about the pros and cons. This will be more obvious later. So the pros of this attack, well, the immediate one is that an attacker does not need to know the key or the security access algorithm. Like, you just don't care. You just like take a hijack a session. That's the name, right? That's where the name comes. And the operation is easily repeatable with consistent timing. I mean, if you have a tool that, let's say, performs a firmware update, right? And you're going to use that to hijack its session, right? Then you can measure how long does it take for that tool since you press start on the flashing process until you can hijack the session, right, when the security access happens. So it is easily replicable. You can do it like easily over and over consistently. Now, the only con is that for every time you want to hijack a security access session, you will need to have the tool. So if you're going to be working on a project where you're going to attempt to hijack a session, let's say twice a day for a month, you're going to need the tool for a month, right? So that's the only con.
Now, Security Hammer is a programming attack or a software attack that Javier once again developed, and it exploits poor implementation practices in state machine logic, specifically for the diagnostics. And before I really explain what exactly SecHammer does, I kind of have to explain the implementation practices that it exploits. So I want you to first think about the tester. And the final step, when the tester sends the key to the DUT, the DUT gives you two options. You can either have the right answer or the wrong answer. But what if you didn't send that final answer? Then you didn't get a right answer or a wrong answer. This might be what Hacker Kitty was trying to point out earlier as well. But back to SecHammer, if you instead of not sending anything, you asked for another seed, you weren't right and you weren't wrong, but you still get another seed. And then you do it again and again. SecHammer does it thousands of times until you have thousands of seeds. And with that, you can look at randomized seeds that I mentioned earlier, and you can see if they are really random. You can try to look for some sort of pattern in them and just gather general information on them.
Yeah. So we are running a little bit tight on time, so we're going to have to speed it up. Nonetheless, again, another blurry image. Hopefully you guys can see some of it. So basically, this is an example of SecHammer. On the first line, we just start a standard diagnostic session. Well, not a standard, 02. So it says, wait, okay, we got the diagnostic session, then we request like seed level 1. Yeah, here's your seed level 1. Here's your seed level 1. I mean, and the wait time, because we are using the standard, but we could go way faster. You can see you cannot probably, but the ECU takes 855 microseconds to reply. We're waiting 30 milliseconds. We could narrow this down to 1 millisecond. So we could be getting around 500 seeds per second, perhaps. I mean, like, this is pretty fast and pretty powerful. And like Ethan said, with this, you can actually get a feeling of the randomness, right, in the security access, the seed key algorithm, which until now was not really possible. Now, does it always work? So we tested more than 40 ECUs, including my own car. I mean, like we have tested like ECUs on the bench, different cars, All the stuff of the 40, 38 were vulnerable. And one of them, we didn't consider it vulnerable because it was just repeating the same seed, 0, 0, 0, 0. Like no matter what, you unplug it, replug it, always the same seed. So we'll just say it's not vulnerable. And now, this is important. Some seeds, actually, they a little bit accounted for this, not like a lot, but they did. So they actually, if you request them the seed again, they send you the same seed again. Now, there's ways around that. We need to remember that diagnostics is actually a state machine. So if you are in a diagnostic session, right, and you ask for a seed, then if you ask again and you get the same seed, you need to change something. Now, what can you change? You can request perhaps security access for a different level, because that would override the seed value, right? Again, we're thinking about poor implementations here. So they have an embedded systems. They have only one variable for seeds. So when you replace it with a different security access, then that gets replaced, right? Or you could try switching to a different session, right? A diagnostic session, because we also said that security access does not carry over to different diagnostic levels. Or you could just let's go now full retard here. You could just disconnect and reconnect from the ECU, right? That takes longer, but still that would work. And the thing is that you don't get locked, right? Like with typical security access, if you send 3 wrong attempts, you got to wait out from 10 seconds to 30 minutes. With this method, you don't get locked out. You just get all the time, all the seeds.
And now SecPuppet combines the SecHammer that I mentioned and the man-in-the-middle attack. And it's divided into 3 primary parts. First of all, it analyzes the randomness, it gets the randomness, and it generates, figures out what kind of seed, or picks out a specific seed that it wants to use using SecHammer. Then we go over to the man-in-the-middle part, and it forces that seed once you're in the man-in-the-middle attack, so that it pulls out a specific one. Now, once man-in-the-middle has given you that seed, and you've, using the process that we mentioned before, found the key for that seed, you can use SecHammer again and force that same seed. And now you have the key, and you can get access to that level whenever you want without the tester using just SecHammer, because you know exactly what the seed that you can get and the key.
So to add a little something to what he just said, so basically what we're going to do is we're going to use SecHammer. We're going to figure out if the randomness is good. We're going to figure out if there's a number that gets repeated more often than the others, or the most repeated number in the randomness. Or we're going to figure out if there's a pattern. If there's a counter that goes up and since reset, then you know the initial value and then you can see it going up. All these are true cases. Now, if you find that value that you already know, then you're going to use the man in the middle. And what you're going to do, he will explain in a second, is you're going to force your own seed, right? And then you're going to get the pre-calculated reply from the tester, and then you will use SecHammer again to try to force the DUT to give you the same seed that seem to appear most commonly, right? Or in the pattern. Sorry, go ahead.
Okay. SecPuppet follows a very similar, thank you, follows a very similar pattern to what was before. There's requesting the seed for security access, goes the man in the middle, then the middle forwards it, requests the DUT receives that seed request, and then it responds with the seed, calculates it before it receives that seed. We force the seed very specifically. Sorry. So it forces the seed very specifically. As I mentioned earlier, it forces the seed for that one seed that we want to have, that one seed that we're going to recreate and reuse every single time. And then once it gets that seed, then it sends it to the tester, and the tester then calculates using the algorithm that we don't know, and then we save that key. We save it so that we can use it whenever.
So really quick, so here would be, right, when the DUT sends its own seed, the man in the middle attacker would replace that seed with the one that we found out that gets mostly repeated, right? Or the most common one or the one we want to find. So then when we give that seed that we want to give to the tester uses that seed, and then it gives us the reply to that seed. What does that mean? The pros. Again, an attacker does not need to know or care about keys or algorithms, right, with this method. This one, unlike security hijack, requires a one-time access to testing equipment, right? Just to do the man-in-the-middle attack to get your seed pre-calculated. And now the cons. The biggest one, obviously, is that the target needs to be vulnerable to SegHammer, right? If you cannot analyze the randomness, the source of randomness, then that's not going to work too well, right? Or if you cannot get it to give you many seeds, right, fast. And then the target needs to have like poor or predictable randomness, because it might be susceptible to SegHammer, but it might actually have good randomness. And a few use cases for these attacks. One would be, this is more rather for testing than for an attacker. It would be like testing the ECU randomness source, right? Like if you get like an ECU from a tier 1, and they are telling you, or you have in your requirements, like, yeah, it should be like truly random, and then you perform this test, and you see it's just sequential based on a timer, on the microseconds, that's the seed, right? Or the ticks, have seen. Then you can tell them like, yeah, this does not meet whatever. Another one would be like reading and writing memory or flash offsets that are like off limits, in the sense of if you get like one of these tools from eBay that allows you to flash your ECU, you could do security hijack, or you could do a SegPuppet or anything. And then you could try to read into the RAM range, which that tool does not do by default, right? Or any other tool. And then performing operations that are not supported by the tester. Like if you know like the payload to send to execute a specific action, but the tool you have in your hands does not do that, you could hijack the session and then send your authenticated command, right? And that was it. We were a little bit over. Thank you very much for attending, everyone. We hope you enjoyed the talk. And if you have any questions, feel free to reach us out. We're going to be around.
Yeah, so if you have any questions, we have a microphone in front. Maybe you can walk up to the microphone in the center. Okay.
Hi, good talk. Given that the system would be vulnerable to the SegHammer, could you just go ahead and do something like rainbow tables, just pre-computed the pre-computation of all the seeds that you send to the testing device, and then simply save it, and then basically use the one that you want to use just when it appears?
So that would be doable. The thing is that that would take too much time, because let's go to this would be for the SegPuppet attack, right? Because on SegHammer you just get seeds, but you want to have a tester pre-calculate the key, right? Sure. I mean, we're talking about a scenario where you do not know the security access algorithm. Correct. Or you do not know the key. So you will have the tester. And the best you could do is like automate the tester starting the process, whatever, right? Or if the tester has literally a command to authenticate, right? Then you could just like hammer the tester with your own seeds. Yeah. That would be an option. I mean, it is doable, but it would be very slow. That would be mostly useful if you have a subset of, let's say, 20 most repeated seeds. Right? Then you want to create a table for all those 20 seeds. That is doable. But if you want to do the whole 4 bytes calculation, that's going to take some time.
Yeah, I mean, if you're sitting in the middle, you could be seeing all the traffic going on and never sending the response, as you just did. So even if that could overcome the good randomness, so you could work maybe with that. So that was just...
I know, yeah. I mean, that should be doable, yes.
Thank you.
So it sounds like you have something to discuss afterwards, off the stage. So I have to kick you off the stage. No. You kicked out the security.
No.
And we will prepare here for the next talk.
This is yours.
Thank you, and applause.
Thank you very much, everyone.